Hello folks, this is the video to help you with the take-home test problem for our Trig unit. And you might be asking yourself, why are we doing this? This doesn't look like Trig. Well, you're right, this is not Trig right here. But these ideas are absolutely crucial for some of the graphing that we do in the Trig unit. And also I just wanted to redraw your attention back to what we've already done because we don't want to forget it, so we're going to do a little practice of it. So, problem number 1 is sketch a graph of the function f of x equals x plus 7 times x plus 2 squared times x minus 3. Now, remember, the first thing we want to do is we want to go in and identify where our zeros are. So, in this case, it's always going to be the opposite of whatever we're adding to our x values. So since we have x plus 7, that will correspond to a 0 at x equals negative 7. X plus 2 will get us a 0 at x equals negative 2, and x minus 3 will give us a solution at x equals positive 3. So the first thing I'm going to do is I'm just going to mark in a scale on these axes and plot those zeros. So we have our three zeros, one at negative 7, one at negative 2, and one at positive 3. But where do we go from here? Well, we need to think of the degree of the function. That is, if I multiplied all of these terms together, what would be the highest power on my x term? Well, I'm taking an x times an x squared times an x. That's going to give me an x to the fourth. So the degree of this function is 4, which means it's going to behave like an x squared function, meaning that if the function is positive, then my tails will both be up, just like x squared. If when I check the degree of my function, if I ended up with a odd number, like a 3, then it's going to behave like a cubic function. But this is a fourth degree function. It will behave like x squared. And so I know that I need to be starting up over here and ending up over there. So whatever it looks like in between, we'll piece together, but I know that for sure. So I'm going to start to the left. I know I'm starting up. And then if you look at that 0, the first one right there, x equals negative 7, notice that the multiplicity of that factor is 1 right there. There's nothing written, but that means it's 1, which means that 0 will cross through the x-axis. So I need to start up, and I need to come down like that, and then I need to curve at some point and approach that next 0. But notice that next 0 has a multiplicity of 2, which means it will bounce. Odd multiplicity will cross, even multiplicity will bounce. So as I turn and go back up, rather than crossing through the x-axis, I touch it and I bounce back down. And then up here, I need to cross at my next 0 and end going up. So I have to cross because that multiplicity is 1, and I have to end up because of the degree of the function and the end behavior that we've already talked about. All right, so that's our graph right there. Notice we have no scale on the y-axis. That's okay. We're just looking at the general shape, end behavior, and zeros of this graph. And we get this little butt shape. So let's go on and look at problem number 2. Number 2 is graphing the reciprocal of this function. And so that means we are taking 1 and dividing it by f of x. So all of those zeros, all of those factors that gave us zeros are now in the denominator, which means they will correspond to vertical asymptotes. So everywhere I got a 0 from the original function, when I do the reciprocal, I'm going to get a vertical asymptote because those are the values where I would be dividing by 0. Boop, 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 boop. So I get 3 vertical asymptotes right there. Okay, so let's think about what else we need to know in order to sketch this function. Well, first off, we're doing 1 divided by whatever that product in the denominator is, which means if we're thinking about a horizontal asymptote, as our x values get bigger and bigger and bigger, that denominator is getting bigger and bigger and bigger, which means our horizontal asymptote, aka limit as x approaches positive or negative infinity, will be 0. So I know my branches are going to level out to the y value of 0 at the ends of my function, the left and the right. So it's kind of like the end behavior for this rational function. Now how do I piece the rest in? Well, I'm taking 1 divided by that blue graph. So wherever that blue graph is positive, my rational function, my pink graph, will be positive. So if I start on the left here, I know my horizontal asymptote is 0, so I can come in like that. As I approach that vertical asymptote, I have to shoot up to positive infinity because I cannot cross that vertical asymptote, and I have to be positive because that blue graph is positive in that entire section. Go to the other side of the asymptote. Well, look, the blue graph is entirely negative there, which means my pink graph has to be entirely negative there. And I have to curve off to either negative or positive infinity as I approach those asymptotes. But since the blue graph is totally positive, I have no choice but to go off to negative infinity. Same thing on the other side right there. So I have to be negative and going down like that. And then finally, all the way to the right, same idea, except now I'm positive because my blue graph is positive. And so we have our pink rational function, and we are happy people. Now, the question on the back asks why it's useful to understand the relationship here between a function and graphing its reciprocal like we just did. Why is that useful for the trig unit? Well, in our trig unit, we do a lot of graphing of reciprocal functions. So, for example, maybe we graph y equals sine of x like we normally would. We'd go 2 pi and pi over 2 and 3 pi over 2. Label that 1, label that -1, and then we would go in and plot our points. Starts at 0, goes to 1, back to 0, down to -1, and then back up to 0. And we could sketch that in like that, kind of like we did with that original blue graph. And then, if we wanted to graph the reciprocal of that, y equals cosecant of x, well, it's the same idea. Anywhere that the original function has zeros will become vertical asymptotes, and so we get those vertical asymptotes. And then anywhere that function is positive, we will remain positive, just like that. Anywhere that function's negative, we will remain negative. And so we can sketch it in and use all the same properties of asymptotes and zeros and positive and negative, just like we did above.